Thank you. Thank the organizers for having me. So this will be for differential equation, partial differential equations are like the elliptic and the parabolic equations, but for manifolds, so I'm more of a hyperbolic person. So this will be a mixture of techniques in mean curvature flows in hyperbolic manifolds, in particular hyperbolic string manifolds of Quasi-Fuchsian type. So here's the basic problem is to study minimal surfaces, or more generally constant mean curvature surfaces in hyperbolic string manifolds. Those surfaces I'm interested in will always be incompressible, closed. So or the genus, high genus at least 2. And those Riemann surfaces come with its own hyperbolic structure, and I want to look at the interaction between, for instance, the conformal structure or hyperbolic structure on the surface and the ambient manifold. So everything I say here will be joint work with Bigo Wang. Anyway, so the assumption is all my surfaces are closed, incompressible high genus, and my string manifold is complete hyperbolic. All right, so let's look at a baby case. So-called Fujian case. So Fujian case, my hyperbolic string manifold is Fujian is actually a product space of surface cross R. So the surface is hyperbolic, so it's totally geodesic. So you can see here's a rough picture. So you have a surface S sits there, and the two conformal infinities. So this is the baby case. You can imagine there's a geometric foliation going from S to both infinities by level sets. And this is still a huge space, the space of all the Fujian manifolds. That's just to identify, it's the same as Teichmüller space. You can look at it this way. So one of my favorite spaces, so the space of all the hyperbolic metrics on a surface up to a equivalent relationship. So this is still a huge space. The real dimension is 6G minus 6. But that's pretty much all I'm going to say about Teichmüller space in this talk. So now let's move to Quasi-Fuchsian case. So I will just use QF. So M is Quasi-Fuchsian, so if it's quasi-isometric to a Fuchsian manifold. So quasi-isometric is quite similar to the previous talk. You have two metrics, they are C0 close. So in the Quasi-Fuchsian, you have two constants. So basically, they are pretty similar if you look far away. So topologically, you still have a surface cross R structure. So here's a rough picture. So you have a convex core, which is in particular. So this is a compact submanifold with convex boundary. So outside of convex core, you have those convex surfaces. They are pretty easy to understand. So, but all the mass, pretty much all the geometric information is contained in this convex core. Part of our motivation is also try to use minimal surfaces or CMC surfaces, try to get information for this convex core. So a basic theorem of Bayes is so-called uniformization theory of simultaneous uniformization theory of Bayes, which is if you pick any two conformal structures, that will be 2 points in Teichmüller space. So you can build a Quasi-Fuchsian string manifold with those two conformal structures as your conformal infinity. So the real dimension for my Quasi-Fuchsians, for the space of all my Quasi-Fuchsian string manifolds is 12G minus 12. So you have a huge space of hyperbolic string manifolds. So here's again a really rough picture. So here's a Teichmüller space. Here's another Teichmüller space. So you have a conformal structure here, conformal structure pick here. So this pair determines points in my Quasi-Fuchsian space. And this diagonal, it is my Quasi-Fuchsian locus corresponding to my baby case, the Fuchsian manifold. All right. So I like to study the minimal surface in Quasi-Fuchsian string manifold. So a basic theorem in the late 70s due to Zheng and Yao, the Sachs-Woolenbach, they showed if you have a quasi-Fuchsian, well, they proved much more general theorem, but let me put in this content. So if you have a Quasi-Fuchsian string manifold, then this convex core as a compact string manifold admits an immersed minimal surface. So you have at least one immersed minimal surface which sits inside the convex core. So we want to basically do a counting of minimal surfaces. So we look at so for a Quasi-Fuchsian string manifold, you might have lots of minimal surfaces. So we consider a smaller space but with the same real dimension. That would be, so I'm looking at a subclass of Quasi-Fuchsian string manifold, which now we call nearly Fuchsian. So that would be in this region. It contains the Fuchsian locus. So the condition is, so if your string manifold admits a surface with principal curvatures within the unit interval, then your string manifold is of this type. So it's an open subspace inside the Quasi-Fuchsian space. All right. So in this space, we try to use mean curvature flow to find minimal surfaces. So here's one of the theorems we proved. So in this case, you don't have to assume much to get long-time existence and the convergence for the mean curvature flow, which is really nice. It has something to do with the specialty of being this type of string manifolds. So let me state the theorem. So string manifold is nearly Fuchsian, so you have at least one incompressible surface of high genus with this small curvature condition. Then you look at a smooth surface, which is a graph over my reference surface. Then my mean curvature flow with this graph as my initial surface has a long-time solution. It's going to drag this initial surface to somewhere. And the evolving surfaces, they stay as graphs over the reference surface. That's pretty easy to prove, actually, pretty standard. And then, so after you have long-time existence, we also showed you can find a subsequence so that this subsequence converges to an embedded, because this is still a graph. So it's an embedded minimal surface. So we can find at least one minimal surface, but we don't know if that's the same one you get from Zheng and Yao, at least not now. All right, so that's the theorem. So more geometrically, because now that deformation theorem is pretty general, because we just start with a graph, and then we don't have to assume the principal curvature being small on my initial surface, as long as it's a graph over some surface with small curvature. So geometrically, there are tons of surfaces, like mean convex surfaces in my hyperbolic string manifold. So especially outside of my convex core boundary. So for instance, if I pick just a mean convex surface away from my convex core, like here, so this is reference surface. I can put reference surface somewhere there as well. It really doesn't matter. So if this is my initial surface, if it's mean convex, then it stays mean convex. It's pretty easy to see. And everything works sort of because we are looking at it. This is a graphical case as well. So those surfaces, they are graphs of height function, which are basically the hyperbolic distance from this reference surface. So in this case, if your initial surface is mean convex, then this height function is a strictly decreasing function. So you can see the mean curvature flow start from here, then drag towards the reference surface, then keep going in this direction until it stays as mean convex, until it hits the until it hits the minimal surface here. So that's the mean curvature flow case. So to make life harder, so we also try to introduce some non-local terms into mean curvature flow. So with non-local terms, there's just difficult to apply maximum principle some of the arguments. So here's so if I insert this non-local term here, so with some condition we can prove theorems like you can prescribe mean curvature function on your 3 manifolds, like a construct surfaces like that. So for instance, here's the one of the theorems we proved. So that's 5 minutes mark, right? Okay. All right. So again, if you have a nearly Fujian 3 manifolds, if you consider smooth function, so that's my prescribed mean curvature function, which the condition is, so the image is in the closed interval which contained in -2 to 2, because all those mean curvatures, well, we have to use this condition to make sure all my evolving surfaces stay in a compact region, so it doesn't drift away to infinity. And we need some gradient bounds, but they are really mild conditions. Then we can construct an embedded surface with that prescribed mean curvature function as my mean curvature function on the surface. And the obvious corollary is I can just pick my constant function between any number between -2 and 2. I can construct a CMC surface which is embedded in my hyperbolic 3 manifold with that particular number. All right, so if I move to 2 and 3 dimension, there's even a smaller class, the so-called Uhlenbeck's almost Fujian manifolds. So you know there's minimal surface. So if you require the minimal surface, certify this principal curvature condition is almost Fujian. So that will be almost Fujian here, nearly Fujian here, quasi-Fujian is everywhere. So one of the open problems is, do you have a way to prove almost Fujian and the nearly Fujian, this is actually the same space? But it's, from mean curvature flow point of view, it's quite difficult to control the principal curvature. So now it's in the work in not much progress status for a while. So just to mention applications from minimal surface to what you know about hyperbolic geometry, here's a baby theorem here. So, well, Uhlenbeck proved that if you're in the almost Fujian case, that minimal surface, it is the only one you can find. So in that case, we can show if you look at the maximum principal curvature of your minimal surface, then you can give this hyperbolic volume of this convex core, which contains all the hyperbolic geometry. So there's the upper bound, there's a top genus here, some constant, and this is a function only depends on this principal curvature. So when you look at as an analyst, you always look at a power series expansion for small lambda 0, small principal curvature. So the expansion looks that way, which means if your minimal surface is really has really small principal curvature, your 3 manifold looks more and more like a the Fujian case, totally geodesic case. So, but so yeah, so that will be all. Thanks.
Questions?
So in the almost Fujian case, yes, it converges. The mean curvature flow converges to this unique minimal surface. But in other case, we don't know yet. So. Right, so it doesn't bounce like this, right? Right, so yeah, so right now let me just say I have the convergence, but I don't know the convergence is experiential. So you mean pinch curves on my surface?
Pinch a curve or degenerate some
Uh, I mean, so there's a, I mean, so if your principal curvature is some epsilon, there's some obvious stuff you can pick up, but if you allow principal curvature reasonable size, it's difficult to see.